Hello, welcome to video number 3/video number 1 of section 4.5/section 4.6. Your book organizes this in a weird way that it kind of like sort of briefly introduces these ideas at the end of section 4.5, but doesn't really give them much time. And then in 4.6 actually talks about kind of what we're going to talk about. So it just makes more sense to combine this, but there's technically a little bit of this in, I think these two facts maybe they give in section 4.5 for some reason. But anyways, remember to like, comment, and subscribe. I feel like I haven't been doing my job as a professional YouTuber by not saying that. But anyways, we will, I guess, get started. So, I just want to go over a couple facts that we already know from looking at the column space and the null space of A. I guess we technically haven't like officially stated them yet because when we sort of went over this, we hadn't yet defined dimension. But fact one, the dimension of the null space of A is equal to the number of free variables in the homogeneous equation, AX equals 0. Yeah, I mean, this sort of just follows from how we find a basis, right, for the null space of A. Remember that, right, we find a basis by looking at the number of free variables, or we find a basis by looking at the number of vectors that pop up in the parametric vector form solution to this, right? So each vector, remember, corresponds to a free variable. And so that's sort of what implies fact one. Fact two, the dimension of the column space of A is equal to the number of pivot columns in the RREF of A. Number of pivot columns in the RREF, that's just sort of follows from, right, how we calculate the column space of A. And so remember, again, we find a basis for the column space of A by looking at just that, right? We calculate the number of pivot columns that appear in the RREF, use that to find our basis from the original matrix. And so each of these is sort of just stating what we already knew, but using this new definition of dimension, which we'd introduced. And so we have two other definitions here that we can officially introduce now, because, of course, leave it to mathematicians to give these two values their own names. So the rank of A is the dimension of the column space of A, so col A or column space, and the nullity of A is the dimension of the null space of A. And so rank we will use more as a definition than nullity, or at least the book thinks we're going to do that. I might use rank and nullity because we'll be talking about the dimension of the null space of A quite a lot. So I might use both definitions quite frequently. So rank is the dimension of column space. Nullity is the dimension of null space. So studying all of this, we get a really interesting relationship between the rank and the nullity, right? Because notice the values of these two things are very related, right? Because how do you determine if something is a free variable? Well, it's a free variable if the corresponding column isn't a pivot column when we look at the RREF. But the dimension of the column space is equal to the number of pivot columns. And so this is the big theorem of all of linear algebra. Let A be an m by n matrix. Now, so notice, if A is a matrix with n columns, then either column has to be a pivot or not a pivot, right? And there's no in between, right? You're either a pivot column or you're not a pivot column. And so that means that the value of the rank of A, which will denote rank A, plus the value of the nullity of A, well, this one is counting the number of pivot columns in the RREF this one is counting the number of non-pivot columns. Since each column has to be one or the other, rank A plus nullity A is equal to n. And so what's so cool about this is that, remember, well, so first off, these set spaces, right, the column space and the null space of A, are in different dimensions, right? This is a subspace of Rn. Yeah, the null space is a subspace of Rn, but the column space is a subspace of Rm, right? Because remember, the column space is this, like the columns of A have length equal to m, and then the null spaces, so like these are two spaces that aren't even in the same dimension normally, and they have this relation, which is, you know, very, very nice. And so it's really awesome that like you kind of get this nice relationship between the two. I think an even cooler, so if you think about A as a linear transformation, right? A is always mapping into Rn. It's mapping into Rm from Rn, right? And so sort of what these things are encoding is like how much of Rn is getting sent to the zero matrix and how much of Rn is getting sent to not the zero matrix, right? Because A is, if you think about A as a linear transformation, then A is mapping Rn to Rm, right? And so basically rank A is accounting for all of the dimension of Rn, if you want to think about it like that, that isn't being mapped to the zero vector. Nullity of A is accounting for all of the dimension of Rn that is being mapped to the zero vector. So yeah, very cool stuff. So anyways, with this theorem, and so there's a mini proof on the worksheet. I think I've basically talked through exactly how you do the proof, so I'll leave that as an exercise for you. We can look at problems now kind of like this, where we can now determine the dimensions of these subspaces. Sometimes, you know, we can learn about the dimensions of these subspaces, sometimes not even knowing, you know, certainly if we know the dimension of one and we know A, we know the dimension of the other, but we'll see from 2 that we can actually learn a lot about the dimensions of these subspaces, not even knowing either. So if we let A be a 3x5 matrix, with rank A equal to 2, then what is the value of nullity of A? So, by the rank nullity theorem, well, we know that 2 plus the nullity of A is equal to 5. And so this means that the nullity of A is equal to 3. And so this means that the dimension of the null space is equal to 3. The dimension of the row space, or sorry, column space, is equal to 2. Second, let A be a 2x6 matrix. What is the minimum possible value of the nullity of A? So to answer this question, so this is of course the minimum possible dimension for the nullity of A. So remember again, rank of A plus nullity of A is equal to 6 by the rank nullity theorem. So what we need to do here is determine the maximum possible value for the rank. And so notice if A is a 2 by 6 matrix, right, that means A has 2 rows and 6 columns. And so that means that if we look at all of the columns of A, right, at most 2 of them can be linearly independent. And so this means that the rank of A is less than or equal to 2, right, because A has at most 2 linearly independent columns. And so this implies that the nullity of A has to be at least 4, because again, remember the sum of these two values has to be equal to 6. So that is the rank nullity theorem. I wrote it here as part 1. There is one more part that we're going to now go over because we have one more interesting subspace which can arise from a matrix. And so we're going to talk about that and then kind of relate it back to some of what we've been talking about here. So I could probably, given the previous definitions we have, I could probably tell you what the term we're going to define is, and you could probably define it for me. So we're going to let A be an M by N matrix. Then the set of all linear combinations of the rows of A is called the row space of A, and we denote it much like we did the column space as row A. So it's basically just the column space but with rows. And we probably could have defined it like that too. The row space is just the column space but with rows. So it's just, you know, the set of all linear combinations of A. And so or the rows of A instead of the columns. And so as a quick example to differentiate, if A is equal to the following matrix, then, so I'll write out the sort of set of vectors comprising both the column space and the row space. So the column space here is equal to the span. And note this part isn't on your worksheet. I just want to use it to sort of differentiate the two. The column space is the span of the vectors comprising the columns of A. So it's the span of these 4 vectors. And the row space is going to be the span of these 3 vectors. And so notice here, again, the row space will be a subset of Rm. So here in this case, it's a subset of R4. And the column space is a subset of Rn. We really should have picked different letters for this, though, because M and N sound way too alike. So here, column space is the span of the 4 columns. Row space is the span of the 4 rows. So much like we did with the column space, we want to find a basis for the row space of a matrix, right? And so it turns out, before I write this, we actually have a way of doing this. And this basically just follows from the fact, right, that row operations on a matrix A are equivalent to just sort of forming linear combinations of the rows. And so finding a basis for the row space actually ends up being straightforward with our row operations, because if two matrices A and B are row equivalent, then their row spaces are the same. And that just follows from the fact that, again, we're getting the rows of B by taking linear combinations of the rows of A. And we also know that if B is a row echelon matrix, that the non-zero rows of B form a basis for the row space of B and the column space, or row space of A, excuse me. So how do we find a basis for the row space of A? Well, we just row reduce until we get to a row echelon form, and we take all of the non-zero columns extending across the matrix. So there's two questions accompanying this example, and so I'll answer the first. So the first question asks, why can't we be 100% sure that the rows of A form a basis for the row space of A? Certainly take a second, pause, think about the two questions on your own. Given this theorem and sort of what we know about bases, you can answer questions 1 and 2. But so question 1, how do we know this isn't just a basis? Well, remember, just by looking at a set of vectors, right? So this statement here is 1/2 of what this would need to be a basis, right? The span of these three vectors is equal to the row space of A. But remember, if I don't know that these three vectors are linearly independent, then there's no way to guarantee that this is, by definition, a basis, right? And in general, looking at a set of vectors and trying to decide if it's linearly independent is not a reliable way of determining linear independence, because it's just generally a hard problem. Like sometimes you can do it, but generally you just want to use row reduction techniques to determine that. So if we want to find a basis for the row space of A, I'm going to erase sort of below this so that I can row reduce A. We're going to need to, by this theorem, row reduce A until we get to a row echelon form. And that row echelon form will give us a basis. And so maybe in the interest of time, this is, I think, a couple steps of row reducing. I will leave the row reducing as an exercise. I've also got the steps in the solutions in the worksheet. So if you want to see those, I will post those at some point. But after row reducing, this is the row reduced matrix I got, which if we're sort of following the theorem, theorem 13, this would be the matrix B in theorem 13. And so what we know then is that the non-zero rows of B form a basis for the row space of A. Which means that I can write with supreme confidence that this, I should write span, row A is equal to the span of those two vectors, and that this set is now a basis because these two vectors are linearly independent and their span is equal to the row space of A. So row space, like I said, not super new from column space. I think with these two things, you just have to make sure, am I working with the rows of A, working with the columns of A, and then how do I go about finding bases for each? And I think the thing that I know would always confuse me with these. So remember, with the row space, I can actually take these columns from B to be my basis. with the column space, remember, I want to look at the pivot columns and then go back to the original matrix A. So always be careful to know, like, when you're taking a basis, what vectors am I choosing? So we'll wrap up, actually we'll wrap up both section 4.5 and 4.6 with this last theorem, which is the rank nullity theorem part 2. And if you're following along in the book doesn't split this up into 2 parts like I did. Basically, the reason I did it is I thought it made a lot more sense to talk about the column spaces and the null spaces and their dimensions first, and then introduce row space. So I didn't really like the order your book went in. But so this is basically just the second thing that the rank nullity theorem in your book proves. I think your book also calls it the rank theorem, but I prefer rank nullity. So we'll let A be an m by n matrix. Then the dimensions of the row space of A and the column space of A are the same. So again, we get this another awesome relation from a matrix, right? That isn't necessarily square, meaning that these 2 spaces aren't even in the same dimension, but their dimensions are always the same, right? So this one is in Rm, this one is in Rn, but again, notice they're, other way around. This one is in Rn, this one is in Rm. But notice, again, that their dimensions are always the same. So to prove this, again, I've broken this down into a couple steps, and I would highly recommend sort of trying to think through it first. So notice that if you go back through the methods of how we calculate the dimensions for each of these spaces, we kind of have the same start, right? I guess, given the trend of how linear algebra works, we calculate the dimensions of both of these spaces by row reducing a matrix. And so we can do it by row reducing a matrix if we want all the way to reduced row echelon form, right? And so notice, well, this one only requires row echelon form. Once we get to row echelon form, if you remember, we're not going to add any more 0 rows than we have. So we could just go all the way to reduced row. And so the reason I want to do that is because it's easier to talk about pivot columns, I think, in reduced row echelon form. But so notice the dimension of row A. So we'll say let B be the RREF of A. So then the dimension of row A, so the dimension of the row space, is equal to the number of non-zero rows in B. Well, the dimension of the column space of A is equal to the number of pivot columns in B. And so if you think about now, I'll draw sort of an arbitrary matrix here. If you think about how row reduced echelon form works, right? Notice that every time I have a non-zero row, if this matrix is going to be in row reduced echelon form, that non-zero row has to correspond to a unique pivot column, right? If it doesn't, well, then the first non-zero entry in the row is too far to the left, and B isn't a row reduced echelon form matrix. But if the leading one is far enough to the right, well, then it has to be a 1, meaning it has to be a pivot column, right? And so, in fact, in the row reduced echelon form in B, these two things are equal, meaning that the dimension of the row space, and so this is actually the answer to number 2 here on the worksheet that I'm writing out, the dimensions of the row space and the column space have to be the same. Meaning, given any matrix A has the same number, always, 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 of linearly independent columns and linearly independent rows, no matter how uneven these two numbers are, right? So A could be a 100 by 2 matrix, right? And so that would be 100 rows and 2 columns, and at most 2 of those 100 rows could be linearly independent. And so not only that, right, if exactly one of the columns is linearly independent from the other, then at most one of those rows could be linearly independent. And so, again, just so cool to see that like a matrix holds this much power. So anyways, that wraps up both sections 4.5 and 4.6. And so next we will move into 4.7.